Okay, hello, dear participants and organizers of the conference. My name is Mikhail Derevyanko. I am from Irkutsk, Russia. First of all, I would like to thank the organizers for the opportunity to present our scientific results. So, I am present the result of temperature influence on the electric impedance of the cobalt-based soft magnetic wires near the ferromagnetic phase transition. So let me remind you that electric impedance is the opposition to alternating current presented by the combined effect of resistance and reactance in a circuit. So we have investigated amorphous cobalt-based wires, which were derived by phase equation from the melt. This slide presents the scheme and the photo of the setup for wire producing. So we have investigated the samples with lengths of 30 millimeters and 180 micrometers in diameter. So you can see some magnetic parameters such as saturation magnetization, positive for C, magnetostriction. So we can conclude that our wires are magnetically soft. So experimental details. These samples were subjected to hair treatment during 5 hours at the temperatures of 523 Kelvin. The purpose of the treatment is to relieve residual quenched mechanical stresses that have arisen during the production of the wires. The spectrograms show that the wires are amorphous even after the hair treatment. After the hair treatment. So there are some experimental parameters. The impedance modulus were measured using an AtC impedance analyzer in the frequency range from 100 kilohertz to 100 megahertz. Probed current was 1 milliampere. Temperature range was 510 and 2 room temperature. While investigation, external magnetic field was applied to the long side of the wire. Its intensity was varied from 0 to 10 ostate. Magnetic hysteresis loops were studied by inductive method. Here you can see the scheme and photo of the experimental setup. So I would like to note the fact that our setup is highly automated. Special attention should be paid to the measuring cell located in the air duct. So here is the measuring cell with the sample that placed in the air duct for heating. As you can see, the cell has one movable contact, so we can apply tensile stresses. The uniqueness of the setup is that we can simultaneously apply external magnetic field, tensile stresses, and heat the samples. The impedance of the amorphous soft ferromagnetics is highly sensitive to these impacts. It has good practical value. So next, we consider in details the temperature influence on the impedance of cobalt-based soft magnetic wires near the ferromagnetic phase transition. Here you can see the temperature dependencies of the impedance derived in different external magnetic fields. So near the phase transition, the impedance undergoes the greatest changes, about 100%, as you can see. So near the phase transition, you can see the inflection point. This point becomes most pronounced when the sample is exposed to the extramagnetic field, which is clearly observed in the case of frequency of 100 kilohertz, this black cube. So also the different temperature dependence in the impedance near the phase transition can be explained in the frame of skin effect. At the frequency of 100 kilohertz, the skin depth is commensurate with the diameter of the wire. Therefore, at a given frequency, the temperature response of the impedance comes from the entire volume of the wire. At the frequency of 10 megahertz, the skin depth is about units of micrometers. In this case, the temperature response of the impedance comes from the surface area of the wire. So the on-T dependencies at the 100 kilohertz can be explained by the following relations. You can see that in the end that temperature dependence of the impedance can be explained by temperature dependence of the magnetization and magnetic anisotropic field. So to method or determine of the direction of anisotropy in the total part of the wire and its near surface part are presented. The wire, due to methods of its production, has different anisotropy in the inner core and outer shell. So the hysteresis loop show us the axial anisotropy prevails in the wire. The type of anisotropy in the near surface part can be estimated from magnitude impedance dependencies derived at the different frequencies. At the frequency of 50 megahertz, when skin effect is strong, we can see the double peak of the magnetic impedance dependency. It's evidence about a present circular component of the anisotropy in the outer shell. At a frequency of 80 or 100 kilohertz, in the presence of the field, especially higher the anisotropic field, the contribution to the temperature change in the impedance from the magnetization of the entire wire volume will prevalate. Here, the temperature dependence of magnetization is presented. It's observed that near the ferromagnetic phase transition, a small inflection is present, like the temperature dependence of the impedance. You can see this inflection. Within the framework of the two-phase model, the experimental dependencies of temperature dependence of magnetization was approximated by Q described by this expression. So where these are the volume fraction, saturation magnetization, Q temperature, and critical exponent of the ith phase respectively. So the maximum value of the correlation coefficient between the experimental and theoretical dependencies are achieved as the ratio of the volume fraction of the phases of 0.4 and 0.6, while the Curie temperature of these phases are the 475 and 481 Kelvin respectively. Thus, the inflection in the temperature dependencies of the impedance can be explained by the presence of two magnetic plates with the different Curie temperature. So it's our result. Some conclusions. So the amorphous of magnetic cobalt-based alloys are highly sensitive to the temperature and magnetic field impedance of these in these samples, highly sensitive. So these materials can be used in different sensors. Also, the impedance temperature study can be used to accurately determine the Curie temperature and other particularities related with the magnetization and anisotropic field temperature change. Thank you for attention. Please question.
Thank you for the excellent talk, Michael. I really enjoyed it. Do we have any questions either? Oh, we do actually. What do you attribute the high temperature difference in magnetization between experiment and theory to? Anna asks.
Could you repeat, please, question?
The question is, what do you attribute the high temperature difference in magnetization between experiment and theory?
Oh, as you can see, the difference is not big. It's experiment and theory has good agreement.
I would probably agree with you, to be honest. Do we have any more questions? Or Anna, do you want to perhaps elaborate on your question? Oh, the higher Curie temperature is what Anna is asking about.
So it's not high Curie temperature for these samples. It's enough. Because it's a ferromagnetic alloys, cobalt-based and ferrum.
Okay. Are there any more questions? Feel free to unmute yourself or ask in the chat. If not,